Hello, and welcome to section 7.3 on trigonometric substitution. In this section, we will consider an integration technique that, for example, allows us to compute the area of a circle or ellipse, which is done via an integral of the form the integral of the square root of a squared minus x squared dx, where a is greater than 0. This method is a special case of one of the most powerful techniques to handle integrals, called change of coordinates. This is given a detailed treatment in Calculus 3. First, recall the substitution rule. The integral of f of g of x times g prime of x dx is equal to the integral of f of u du, where u is equal to g of x. This technique helps us to recognize the antiderivative of a composite function, and choosing an appropriate u simplifies the integrand. It turns out that reversing this procedure sometimes leads to a simpler integrand. Let's make this precise. Begin with an integral, the integral of f of x dx. Now suppose that x is a function of another variable, say t. So x is equal to g of t for some function g. Then dx is equal to g prime of t dt, and we can rewrite our original integral as the integral of f of x dx is equal to the integral of f of g of t times g prime of t dt. This procedure is sometimes called an inverse substitution. Note that the right integral in the equation is an integral in the new variable t. Once you solve this integral, your antiderivative will also be a function in the new variable t. But our original integral was in terms of the variable x. Thus, we need to be able to rewrite everything in terms of our original variable x. Recall that the variables x and t are related by the equation x equals g of t for some function g. So to be able to revert back from the variable t to the variable x, we need to assume that g has an inverse, or that g is 1 to 1. Let's consider an example to see all of this in action. Consider the integral from before, the integral of the square root of a squared minus x squared dx, where a is greater than 0. Note that none of our previous integration techniques work for this integral. Let us perform an inverse substitution. Bear with us as we will motivate the reasons for our choices shortly. Set x equal to a sine of theta, so dx is equal to a cosine of theta d theta. Now x is a function of theta. Remember, at some point we will want to convert back to our original variable x. So we will restrict our range of theta to negative pi over 2 is less than or equal to theta, which is less than or equal to pi over 2, as sine of theta is 1 to 1 on this range. It passes the horizontal line test. We now input x equal to a sine of theta and dx equal to a cosine of theta d theta into our integral. We get the integral of the square root of a squared minus x squared dx is equal to the integral of the square root of a squared minus a sine of theta squared times a cosine of theta d theta, which is equal to the square root of a squared times 1 minus sine squared of theta times a cosine of theta d theta. We now use the identity 1 minus sine squared of theta equals cosine squared of theta, and we get the integral of a squared cosine squared of theta times a cosine of theta d theta, which equals the integral of a cosine of theta times a cosine of theta d theta, which equals the integral of a squared times cosine squared of theta d theta. Note that the second to last equality makes sense because a is greater than 0 and cosine of theta is greater than or equal to 0 for our restricted range negative pi over 2 less than or equal to theta less than or equal to pi over 2. We are now able to handle the furthest right integral using the techniques of the previous section, and in particular a half angle identity. The integral of a squared times cosine squared of theta d theta is equal to the integral of a squared over 2 times 1 plus cosine of 2 theta d theta, which equals a squared over 2 times theta plus a squared over 4 times sine of 2 theta plus c. So we have that the integral of the square root of a squared minus x squared dx is equal to a squared over 2 times theta plus a squared over 4 times sine of 2 theta plus c. But note the left integral is in terms of x, so we must convert the right-hand side of the equation in terms of x. Recall that x equals a sine of theta, and so we can solve x equals a sine of theta if and only if sine of theta equals x over a, which is if and only if theta is equal to the arc sine of x over a. This is why we restricted to negative pi over 2 less than or equal to theta less than or equal to pi over 2, so that sine of theta is invertible. This handles one term in a squared over 2 times theta plus a squared over 4 times sine of 2 theta plus c. But what about sine of 2 theta? To deal with this, recall the identity sine of 2 theta is equal to 2 times the sine of theta times cosine of theta. We just saw that sine of theta equals x over a, but what about cosine of theta? To deal with this, recall that sine of theta equals x over a, which equals the opposite over the hypotenuse. So we can form the following right triangle. Now note that cosine of theta equals adjacent over hypotenuse, which equals the square root of a squared minus x squared divided by a. Therefore, sine of 2 theta, which equals 2 sine of theta cosine of theta, equals 2 times x over a times the square root of a squared minus x squared divided by a, which equals 2x times the square root of a squared minus x squared divided by a squared, and hence the integral of the square root of a squared minus x squared dx equals a squared over 2 times theta plus a squared over 4 times sine of 2 theta plus c, which equals a squared over 2 times the arc sine of x over a plus a squared over 4 times 2x times the square root of a squared minus x squared divided by a squared plus c, which equals a squared over 2 times the arc sine of x over a plus x times the square root of a squared minus x squared plus c. We now revisit the burning question. Why did we set x equal to a sine of theta in the above example? The moment where this was most useful was at this key step. The integral of the square root of a squared times 1 minus sine squared of theta times a cosine of theta d theta is equal to the integral of the square root of a squared times cosine squared of theta times a cosine of theta d theta, which equals the integral of a cosine of theta times a cosine of theta d theta, where we use the identity that 1 minus sine squared of theta equals cosine squared of theta to eliminate the radical in the integral. Notice that the form of the left-hand side of this identity bears a similar resemblance to the radicand in the original integral, a squared minus x squared. Thus we made the choice x equal to a sine of theta, so we could use a trigonometric identity to eliminate the problematic radical. The following table shows a list of effective trigonometric substitutions for integrals of the given expressions. The way to remember which substitution to use is to remember the identities on the far right of the table and to compare them to the form of the expression on the left of the table. To summarize, here are the basic steps to successfully perform a trigonometric substitution. 1. Choose an appropriate inverse substitution according to the table. You should be choosing the appropriate substitution according to whichever trigonometric identity matches the form of the integrand. 2. Convert the integral and solve the resulting trigonometric integral. 3. If the original integral is an indefinite integral, then you must convert back to the original variable that you started with by using one of the following triangles. But what if you are given a definite integral? Well, it turns out that you do not need to do step 3. Let's look at another example. Take the integral from 0 to 1 of the square root of x squared plus 1 dx. None of our previous methods work for this integral, so we wish to perform a trigonometric substitution. Note that the form of the radicand x squared plus 1 matches that of the identity tan squared of theta plus 1 equals secant squared of theta. Thus we make the substitution x equal to tan of theta with negative pi over 2 less than theta less than pi over 2. So dx equals secant squared of theta d theta. We input this into our original integral, but notice that we have to convert the limits. The integral from 0 to 1 square root of x squared plus 1 dx, which equals the integral of the square root of tan squared of theta plus 1 times secant squared of theta d theta. For the lower limit, we must solve tan of theta equals x equals 0, and for the upper limit, we must solve tan of theta equals x equals 1. So we compute the arctan of 0, which is 0, and arctan of 1, which equals pi over 4. Thus, the integral from 0 to 1 of the square root of x squared plus 1 dx equals the integral from 0 to pi over 4 of the square root of tan squared of theta plus 1 times secant squared of theta d theta. Now we just need to compute the definite integral on the right, and we are done. Notice that the limits of the right integral lie within our range, negative pi over 2 less than theta less than pi over 2. So everything makes sense. We now use the identity tan squared of theta plus 1 equals secant squared of theta, and we get the integral from 0 to pi over 4 of the square root of secant squared of theta times secant squared of theta d theta, which equals the integral from 0 to pi over 4 of secant cubed of theta d theta, which equals square root of 2 over 2 plus the natural log of square root of 2 plus 1. We omitted the details for solving the integral 0 to pi over 4 of secant cubed of theta d theta, but recall from the previous section that this is done by using integration by parts.